Welcome back to section 8.3, part 3, hypothesis testing for one sample mean. Let's repeat our problem that we were working with on the previous page where Bob was improving the production process. We'll still do our same requirement checks. We will be looking for those because you want to make sure you're using the right tool on the right problem. Again, the null and alternate hypotheses, everything is still the same as we've done before. But now we're going to get some help from the calculator. So we're going to turn the calculator on. And here was our test statistic from that last problem. Let's go ahead and do stats, tests, and we're going to run the t-test program. And the reason is we're doing a hypothesis test for a population mean. The population standard deviation is unknown, but we do know this sample standard deviation. So we'll do the t-distribution, we'll check our requirements, and then we'll run the t-test. Okay, so we're running the t-test, and let's see what happens here. Again, if I had the actual list of data, I would select the data option and then tell it where that list of data is, list 1, for example. But I don't, so we're going to go back in and readjust our numbers. So mu is 8.50. X bar, good thing we wrote it down, is 8.21. Our sample standard deviation was, oh, I didn't write that one down. S equals, let me go back to that previous page. .86. That's an S, by the way. So 0.86, N was 47. And this time we're doing for our alternate hypothesis to see if mu is less than the number 8.50. And remember, mu naught stands for the number 8.50 because that's what we told it. So we want mu less than 8.50. And let's calculate. And notice that we get the exact same test statistic we got by hand. And we also get the p-value, which is good. And notice how that p-value, on the last activity, we said it had to be somewhere between 0.01 and 0.025. Guess what? It's right in there as we said it should be. So let's write this down. We're going to write down what test we ran. So t-test. Our test statistic is negative 2.31 to 2 decimal places. Our p-value is 0.0127, if you want to go that far. And if we do the traditional way, we could still do that. We'd still have to find our critical value, but now we know the test statistic, and this guy's in the critical region, so we would reject H naught. But some of you are going to start to move over to the p-value method and just take the p-value and compare him to alpha. So our p-value of 0.0127, how does that compare to the alpha of 0.05? And the answer is it's a big less than. So we, once again, reject H naught. There is enough evidence to conclude that Bob's new method has reduced the mean assembly time. All right, hope that's made sense. Now it's time for you to try some problems. And I'm going to let you use your choice of traditional method or the p-value method. And another true story, Bob is my father-in-law, and he worked as a mechanic. He also worked as a truck driver for many years. So this problem refers to him as well, so a nod to him. Truck drivers have claimed that if the highway speed limit is raised to 75 miles per hour in a certain area, there will be fewer speeding tickets issued to truckers. An examination of traffic citations showed that before the speed limit was raised, the mean number of traffic tickets issued to truckers was 45 per week. A random sample of 32 weeks chosen from the time after the speed limits were raised had a sample mean of 40 with a sample standard deviation of 8. Use a 5% level of significance to test whether the data supports the trucker's claim. Interpret your answer in real-world terms. So I'm going to pause the video, let you work on this problem, but we will come back and talk about what we found out together, make sure you're doing it right. Okay, let's come back together and see what you did. So I'll do a quick summary of my work. So we had a random sample and our sample size was 32, which is greater than or equal to 30. So we are satisfying the central limit theorem. So we're good there on the requirement checks. I wrote down all of my known information and notice that 75 was a number in the problem, but I didn't actually use him because it's only 75 miles per hour, where what I'm really talking about is the number of tickets issued. So even though 75 was a number in the problem, he was not an important number. So the trucker's claim was that the number of traffic tickets would decrease, that we'd have fewer traffic tickets. So that tells me that my alternate hypothesis is that the average number will be less than what it normally is, which is 45. So my null hypothesis is that it is 45, or if you want to get really super technical, mu is greater than or equal to 45. So traditional method, we say that n is 32, so we'll have 31 degrees of freedom on a 5% level of significance and a left-tailed test using the t-distribution. So 30 degrees of freedom and 5% of the area in one tail would be 1.697. But since it's a left-tailed test, left of 0 is negative numbers. So we get our critical value, which we'll mark on the picture. Well, then I ran the t-test program and found out that t is negative 3.54, which puts him here, well inside the critical region. So we will reject H naught. There is enough evidence to conclude that the average number of tickets has decreased after the speed limit was raised. Now, if you do the p-value method, you still need to give me the test statistic, and you still need to give me the p-value. Remember that p-value is short for probability value. And one of the most common mistakes I see here with students is they'll see this and they'll find the p and they'll tell me that it's 6.51. But remember, probability can be no larger than 1. So if you see something like that, keep reading your number and look for this guy. This tells me he's in scientific notation because he's so small. So this e minus 4 means 6.51 times 10 to the negative 4th power. So we're going to take this number and divide by 10 times 10 times 10 times 10, which gives me this super small number of 0.000651. So be careful with that. Students often mistake that. And so our p-value, how does that compare to our alpha of 0.05? It's way less than. And if the p is low, the null must go. We reject the null hypothesis and get the exact same conclusion. So let me do one more example with you before we turn you loose. So let's take a look at example 4 from the next page. Okay, I'm going to have you read it and then decide whether we can use this, and we'll pick up there in just 1 minute. So what did you come up with? Hopefully you noticed that the mean number was 172. The random sample, oh, that's good. So we had a random sample of 15. And the sample mean, so let's use the correct symbol for that, is 195. And a sample standard deviation of 36. Alpha is 1% or 0.01. And we saw that, oops, the random sample and n was 15. Sorry about that. Okay, so are we good to go? And the answer is no, because having a random sample is important, but you also need to check the second requirement. Is n greater than or equal to 30 or normally distributed? In this case, no, n is 15, which is less than 30, and it's not known to be normally distributed. So actually, this problem is easy because he does not meet all the requirements. Okay. So if he doesn't meet the requirements, tell me so, and then stop. The problem's done. Only continue and work if we meet the requirement check. Okay. All right. And last thing I wanted to do, we'll just stop there and we'll see you in the video. So what I want to do now is have you work on examples 5 and 6, solve these problems, and then snap a picture and upload it for our chapter activity work. Okay. See you in chapter 9.